The next few weeks, you'll be designing and building a balsa wood glider. So let's talk about how gliders maintain stability in straight and level flight. While airplanes and gliders share many design, aerodynamic, and piloting factors, the lack of an engine fundamentally changes the way a glider flies. Since there's no engine taking up space, a glider is sized around the cargo it carries. The fuselage is designed to be as small and light as possible, and the surface of the glider's fuselage is designed to be smooth, allowing the plane to fly through the air with little drag. Notice on this glider the elevator is on top of the empennage. This is so the elevator is not affected by turbulence of the wings. Gliders have no engines to increase velocity and thrust, which, as we've discussed, velocity is one of the primary factors in achieving lift. So the only tool they have to increase or maintain velocity is the force of gravity pulling them to Earth. Long-distance gliders will glide steadily downwards at an angle from the horizontal called the glide angle. Using properties for right triangles, we can easily determine the length of flight from the starting altitude and glide angle. Pilots must have an energy source to maintain altitude, so they'll often look to sources of natural lift to increase their time in the air. Effects such as thermals, a rising mass of buoyant air, or updrafts at the edge of a cliff or hill will push the glider to a higher altitude, allowing the glider to stay airborne longer. Your balsa glider will not have access to naturally occurring rising air to help it maintain flight, so it will achieve its maximum distance by following its glide angle in straight and level flight. As passenger aboard our gliders, they'll need to be inherently stable in pitch, roll, and yaw to maintain long-distance flight. There are different types of stability, including static and dynamic stability. We focused and will generally continue to focus on planes in equilibrium. Planes can be statically unstable, also called negative static stability, which means the plane will continue toward instability in the event of disturbance. Planes may be designed to be statically unstable to increase maneuverability. Neutral static stability refers to a plane that will maintain its initial disturbed state after a disturbance, neither returning to equilibrium or tending towards further disturbance or instability. Dynamic stability is about change over time. A statically and dynamically stable plane will have some oscillations after a disturbance, but each oscillation will be smaller, bringing it back into equilibrium. A plane that has static stability but neutral dynamic stability will continue to oscillate at the same rate or period after an initial disturbance. A plane that is statically stable and dynamically unstable will have continually divergent oscillations, but the plane will attempt to reach equilibrium in pitch in the direction of each oscillation. Movement in yaw refers to the left and right movement of the aircraft. An aircraft always has the tendency to turn the longitudinal axis of the aircraft into the relative wind. Air pressing into the vertical parts of the empennage will naturally cause the plane to turn back into the wind. This weather vane tendency is similar to the keel of a ship and exerts a steadying influence on the aircraft laterally about the longitudinal axis. Example of design adjustments on the B-17 aircraft between models. The size of the vertical stabilizer was increased and the rudder size was reduced. This helped to maintain yaw stability. Pitch refers to the up and down movement of the aircraft. When discussing pitch stability of an aircraft, one of the major concerns is avoiding stall. Stall occurs at a critical angle where lift suddenly drops, which is the force keeping you in the air. If lift drops, the weight of the aircraft, or gravity, will bring the aircraft to ground. It can be really difficult to regain control after stall, so it's generally avoided at all costs, especially in mission-critical situations. Think about fighter jets. So weight and balance of the aircraft must be closely monitored. The center of gravity range is unique to each aircraft and must be carefully considered. The pilot, fuel, wings, and storage are generally within the center of gravity range because these things change over time and you want to maintain balance and stability. Refers to the side-to-side movement of the aircraft. Lateral stability has to do with the wing configuration. High-wing aircraft are naturally stabilizing and experience a natural pendulum effect with mass under the wing attempting to bring it back to center. Dihedral wing has wingtips that are lifted. Dihedral wings help to increase stability because the effective angle of attack changes with roll. As one wing gets closer to vertical, the angle of attack is closer to zero, causing it to have little impact on lift. Thus, the other wing is achieving more of the lift, causing an upward force, tilting or rolling the plane back in the other direction. However, too much dihedral will cause you to overbalance. Dihedral wings is the number one way to stabilize a plane and roll. You can have different types, including no dihedral or a flat wing, straight dihedral where the entire wing is angled, tip dihedral where only the part of the wing is angled up, or polyhedral where there are multiple angles on the wing. Greater wing area provides more lift. We can calculate the wing area by multiplying the span times the average chord width. For this aircraft, the wing area is 50 feet span times 2 feet average chord for 100 square feet. For this aircraft, the wing area is 36-foot span times the 5-foot average chord width, giving us a wing area of 180 square feet. In theory, this plane would be better at generating lift because it has more area. However, the aspect ratio is another important quality to consider. It is a ratio of the span from tip to tip to the average chord width. Note, the span does not include the wingtips if there are any. The higher the aspect ratio, the higher the lifting efficiency. The aspect ratio is the square of the span divided by the wing area. For a rectangular wing, this reduces to the ratio of the span to the chord, or you can say it's equal to the span divided by the average chord width. Long, slender, high aspect ratio wings have lower induced drag than short, thick, low aspect ratio wings. Induced drag is a three-dimensional effect related to the wingtips. The longer the wing, the farther the tips are from the main portion of the wing, and the lower the induced drag. A lower lift-to-drag ratio will correspond to greater efficiency. For this example, the aspect ratio is the span of 36 feet divided by the average chord width of 5 feet for an aspect ratio of 7.2. Example, the aspect ratio is 50 feet divided by the average chord width of 2 feet for an aspect ratio of 25. So which plane will have better lifting efficiency? More area put into span leaves less turbulence and thus is more efficient. So this plane would be more efficient. However, a longer wingspan makes a plane less maneuverable. So an engineer must optimize the area and aspect ratio to achieve the design objective. Consider a commercial aircraft is going to give more weight to stability and efficiency than perhaps a military aircraft or fighter jet whose primary objective is to succeed in their mission, so maneuverability may be more important. Airplanes come in different configurations. Here are two very common shapes, the elliptical and straight. The elliptical wing helps to reduce drag on the end. Think of air-tip vortices. Lifting line theory shows that the optimum or lowest induced drag occurs for an elliptic distribution of lift from tip to tip. The efficiency factor is equal to 1 for an elliptic distribution and is a value less than 1 for any other lift distribution. For standard rectangular wing, the efficiency factor is about 0.7. The outstanding aerodynamic performance of the British Spitfire of World War II is partially attributable to this elliptical wing, which gave the aircraft a very low amount of induced drag. Helps to increase lifting efficiency due to the balance between the wing area and aspect ratio. Talked about with the winglets, reducing tips helps to increase performance of the plane. The swept-back wing and delta wing configuration help to simulate this objective in another manner.